everyone, welcome to Saimedha Koti, Hyderabad. In this session, I would like to discuss about gunshot bits in torque slip characteristics of the 3-phase induction motor. So, let us start from the question number 1. The question 1 is the torque rotor impedance of a slip ring induction motor is 0.1 plus j 0.6 ohms per phase. The resistance per phase to be inserted into the rotor to get the maximum torque at the time of the starting should be option 1 0.1 ohm, 0.3 ohms, 0.4 ohms and 0.5 ohms. So, per slip ring induction motor, okay, for the slip ring induction motor, so maximum torque, okay, slip corresponding to maximum torque produced by the motor, S maximum is equal to the R2 plus RE divided by the reactance, the X2 values, where S maximum is the slip corresponding to the maximum torque. So, this is the slip the corresponding to maximum torque produced by the motor. So, T maximum, and R2 is the rotor resistance per phase and RE is the external resistance to be inserted into the rotor, whereas X2 is the standstill reactance per phase. So, this is the maximum torque. So, let us assume it is the example point. So, assume as this one is the equation 1. So, maximum starting torque occurs when the S maximum is equal to the 1. So, maximum starting torque, we know that. So, maximum starting torque, this maximum, the starting torque, the torque occurs at S maximum is equal to, so this is the at S maximum, so that is equal to the 1. So, assume this is the equation number 2. So, from 1 and 2 equations, okay, from 1 and okay, 2 equations, so we get the R2 plus RE divided by the X2, that is equal to the 1. So, let us substitute the given values in this equation. So, this one is 0.1 is the rotor resistance per phase R2 and 0.6 is the rotor reactance, the per phase value R2 plus. So, R2 is a 0.1 plus RE is the 0. RE we need to find out, and X2 is a 0.6 is equal to the 1. So, therefore, RE is equal to 0.6 minus 0.1. So, therefore, RE is equal to the 0.5 ohm. The external resistance to be inserted into the rotor, so that is equal to the 0.5 ohms is the correct answer for this question. And next, let us solve the question number 2. The question is the maximum torque in an induction motor depends on the frequency, supply current, rotor resistance and the stator inductance. So, maximum torque in case of the induction motor, what is the equation of the maximum torque? So, T maximum is equal to 180 by the 2 pi ns, where ns is the synchronous speed. So, E2 square the divided by the 2x2. So, this one is the E2 pi ns into E2 square divided by 2x2. E2 is a rotor EMF per phase, X2 is a standstill reactance per phase. So, this equation that can be written as the T maximum is equal to the 180 the divided by 2 pi, where ns is equal to 120 F by P. So, multiplied by E2 in terms of the applied voltage, some constant K, the V1 square divided by the 2 into the 2 phi F, okay, L2. So, L2 is a leakage inductance, where F is a frequency. So, now here T maximum, all the terms are constant except voltage and frequency. So, by using this equation you can write the maximum torque of the induction motor. So, during operation of the motor, so maximum torque is directly proportional to square of the voltage and also directly proportional to the square of the frequency. So in this question mention that frequency, the rotor resistance, the supply current, the stator inductance, maximum torque depends on the applied voltage and also frequency. By using this equation, it also depends on the rotor EMF and the rotor reactance. But in the options mention that the rotor resistance, it is not correct. Why? Because the maximum torque is independent of the rotor resistance. Supply current is also not correct, and stator inductance. So see this equation, the maximum torque is inversely proportional to the square of the frequency. So it depends on the frequency parameters. So option the 2 is the correct. And next let us solve the question number the 3. The 3 phase, okay, it is the 3 phase. The induction motor is so designed that rotor should have under running conditions. Okay, so under running condition, running conditions. So what is the requirement? Okay, here maximum torque that should be T maximum, okay, should be the high values. So under running condition, maximum torque should be high. So we know maximum torque T maximum is equal to 180 by 2 pi ns multiplied by E2 square divided by the 2x2 values, the 180 by 2 pi ns, the E2 square by 2x2 value. So when to get maximum torque high, the reactance term should be the low values. Okay, this one is a high resistance, low resistance, high reactance, okay, this high reactance and the large slip, and this one is the 3-phase induction motor is so designed, so that should have the under running conditions. So next one, this one is a maximum torque should be high, and one more condition, the starting torque is the low value. So this is also required. Maximum torque should be high and starting torque is low. So starting torque produced by the motor directly proportional to the rotor resistance. So to get the starting torque is a low under running condition. So resistance term should be low. So that is so we are to get the low starting torque. The low starting torque under running condition. The starting torque under running conditions. So under running condition. So this is the resistance term. Okay, R2 is the low value. So now answer for this question, low resistance is required. So it is not mentioned, suppose high reactance is given. So high reactance, the maximum torque is low. It is not requirement. So now suppose low reactance is given, that is the right answer. But in this question mentioned that high resistance, low resistance, high reactance and large slip. So answer for this question, here option 3 is the correct. So under running condition, the maximum torque should be high, the starting torque should be the low. So to get the low starting torque under running condition, what is the requirement? The low resistance value is required. So and next one, question number 4. High starting torque can be obtained by the 3-phase induction motor, increasing the rotor resistance, the decreasing the rotor resistance, increasing the rotor reactance, the keeping the rotor resistance constant. The starting torque produced by the motor is directly proportional to the rotor resistance R2, where R2 is the rotor resistance per phase value. So as rotor resistance is high, then what will happen? Starting torque produced by the motor will be increased. So high starting torque can be obtained by increasing the rotor resistance. So option increasing the rotor resistance, option 1 is correct. And next let us solve the question number 5. So if the supply voltage of 3-phase induction motor is increased to 2 times, then the torque is option 1 increased to 2 times, increased to 4 times, increased to 2 times and decreased to 2 times, decreased to the 4 time. So supply, what is the relation between supply voltage and the torque produced by the motor? So now this torque is directly proportional to the square of the applied voltage. So this torque produced by the motor is directly proportional to the square of the applied voltage. So from here we can get the T2 by T1 is equal to the V12 divided by V11 the whole square. So mention that the torque produced by the motor is the increase. This one is produced by applied voltage of the motor increased by 2 times. So T2 divided by T1 the is equal to 2 times of the V11 divided by V11 the whole square. So V1 is a cancelled out. Okay, T2 is equal to the 4 times of the T1. So answer for this question increased to 4 times. So option the 2 is correct for this question. And next let us solve the question number 6. So when supply voltage voltage to the induction motor the reduced by 10%, then the maximum torque will decrease by approximately option 1 5%, option 2 10%, option 2 20%, option 3 20% and option 4 40%. The same concept, the torque, the relation between the torque and supply voltage. Torque is directly proportional to the square of the applied voltage. So this equation can be written as T2 by T1 is equal to the V12 divided by V11 the whole square. So now simplify here. So first substitute all the values. So applied voltage reduced by 10%. So that means the given in the question the applied voltage in the case 2 is equal to 0.9 times of the 0.9 times of V11. So T2 divided T2 is equal to the T1. The V12 is a 0.9 times of the V1 divided by V1 the whole square. The V1 is a cancelled out. So therefore T2 is equal to 0.81 times of the T1. So this equation is required to answer this question here. So initial value is a 1 per unit and final value is a 0.81 per unit times. So now decrement in per unit value, okay, in the per unit value, so that is equal to 1 minus 0.81 times. So decrement in the per unit value in that per unit value is equal to 1 minus 0.81. So this is equal to 0.19 per unit value. But we required decrement in the percentage, okay, in the percentage value. So this is the initial value, higher value minus lower value, initial value minus per unit, and decrement in the percentage value, per unit value multiplied by 100. So 0.19 multiplied by 100, so it is equal to 19%. So question is approximately, so this one decreased by, so 20%. So option 3 is a correct for this question. And next let us solve the question number 7. The starting torque of induction motor is maximum, the maximum. So rotor resistance is 1.414 times of the rotor reactance, and this rotor resistance is the twice the rotor reactance. The rotor resistance is half of the rotor reactance. The rotor resistance equal to the rotor reactance. The maximum starting torque, okay, this maximum, the starting torque of the motor. So starting torque is maximum. So this starting torque is maximum. So when the S maximum is equal to, when the S maximum is equal to the 1. So this S maximum means the slip corresponding to maximum torque. So this is equal to R2 by the X2, the is equal to the 1. So therefore the rotor resistance is equal to the rotor reactance parameters. So always rotor resistance is equal to the rotor reactance, but not the rotor reactance is equal to the rotor the resistance parameters. So option for this question, option 4 is correct. The rotor resistance equal to the rotor reactance parameter. And next let us solve the question number 8. The torque developed by the 3-phase 400 volts induction motor is the 100 Newton meters. If applied voltage is reduced to the 200 volts, the developed torque will be option 1 50 Newton meters, option 2 25 Newton meters, option 2 200 Newton meters, and option 4 62.5 Newton meters. So in this question, first one, at applied voltage the V11 is equal to the 400 volts, okay, at this case the torque produced by the motor is equal to 100 Newton meters. Now applied voltage the increased from applied voltage reduced from 400 volts to the 200 volts. So this we require torque produced by the motor. So what is the value of the torque produced by the motor? So we know the relation between the applied voltage and torque produced by the motor. So torque produced by the motor the directly proportional to square of the applied voltage. So therefore the T2 divided by T1 the is equal to the V12 divided by V11 the whole square. So where T2 the T1 is equal to the T1 is a 100 Newton meters, 100 Newton meters is equal to applied voltage in the second case the 200 okay, divided by the 400 okay, whole square. So 1 by 2. So T2 is equal to 1 by 4 multiplied by 100 Newton meters, so that it is equal to the 25 Newton meters. So answer for this question the 25 Newton meters is a right answer. And next let us solve the question number 9. In an induction motor, if the flux density is reduced to 1/2 of its normal value, then the torque will be option 1 the reduced to 1/2, the reduced to 1/4, the remains unchanged, increased to the 4 times. So in stable operation of induction motor, okay, in the stable the operation of the induction motor, so this is the torque is okay, torque is equal to the here 180 by okay, 2 pi ns, okay, this ns the SE2 square okay, divided by R2 value. So Sx2 square is a very low as compared to the R2 square. So that's why we can neglect the R2 square in the denominator, Sx2 square in the denominator. That's why. So this is the torque equation in the stable operating mode. Stable operating means so nearer to okay, low value, nearer to the low value of the slip, low value of the slip of the motor, or the nearer operation nearer to synchronous speed, operation of the induction motor okay, nearer to the synchronous speed of the machine. So for low value of the slip or whenever whenever the induction motor is operated nearer to the synchronous speed, the slip of the motor is the low. For low value of the slip, the torque is directly proportional to the slip of the motor. So this one is whenever torque is directly proportional to the slip, this operation is known as the stable operation of the induction motor. For stable operation of induction motor, torque is equal to 180 by 2 pi ns into SE2 square divided by the R2 values. So this equation can be rewritten as, so that is T is equal to 180 by the 2 pi ns, okay, this one S can be written as the S is a ns minus n the divided by ns multiplied by the E2 square by R2 square. E2 square can be written E2 square the divided by the R2 values. So this T is equal to 180 by the 2 pi ns, okay, where ns is equal to 120 f by p. So into, so this one is the ns minus n. So this ns minus n is known as, it is a slip speed of the motor, the slip speed of the motor, where ns is equal to the 120 f by p. So now this one is okay, n is a k into v1 square the divided by R2 values. So if we remove all the constant, then we will get the proportionality. So during operation, okay, this one is the during operation of the motor, operation of the motor. So this torque is the directly proportional to the V1 by F the whole square ns minus n, where ns minus n is a constant, that is the slip speed of the motor. So by using this, what I conclude, so when ns minus n is a constant, so torque is when ns okay, slip speed of the motor is a constant, so then the torque is a directly proportional to V1 by F square. Now V1 by F is a maximum, the flux density of the core, B maximum square. So therefore this you can write T2 by T1 is equal to the B maximum 2 by B maximum 1 the whole square. So B maximum 1 whole square. So now this is the flux density is reduced to 1 by half. So now this is equal to T2 by the T1 the is equal to, so 1 by 2 times of the B maximum 1, the B maximum 1 whole square. So this value is equal to, so B maximum is cancelled out, so it is a 1 by 4. So therefore torque reduced by 1 by 4th is the right answer for this question. So 1/4 is the reduced to 1/4. So that is the right answer. So answer for this question, option 2 is the correct. And next let us solve the question number 10. The torque slip characteristics of 3-phase induction motor at maximum torque. Okay, D, the differentiation of the torque with respect to the slip is maximum. The differentiation of the torque with respect to the slip is 0, and differentiation of the torque with respect to the slip with respect to the torque is 0. The slip is maximum value. So we know maximum torque produced by the motor, okay, T maximum. So actually this one is a here the 180 by, okay, 2 pi ns, okay, E2 square by 2x2 value. This is the formula to find out the maximum torque. But how we got this formula? Exactly in that we know torque equation, the 180 by 2 pi ns, okay, s E2 square the divided by R2 square plus, okay, sx2 whole square. Now in this formula torque is the function of the slip. So to get maximum torque, so to get maximum torque condition, okay, this maximum torque condition, so what we have to do, so differentiation of the function with respect to variable and equal to the 0. So by solving this, okay, we can get, so by solving, so we get the this one is the sx2 the is equal to R2 values. So where S is equal to, S maximum is equal to the R2 by the x2 values. Okay, this one is the, so this is nothing but slip corresponding to the maximum torque. So if we substitute this, okay, condition in this torque equation, so we will get the maximum torque of the motor. Suppose if I substitute here 180, there is a 180 by the 2 pi ns, S maximum you can write S maximum E2 square, the R2 square plus S maximum the x2 whole square. So put the S maximum is equal to the 180 by, okay, 2 pi ns, okay, this 2 pi ns. So S maximum is equal to R2 by x2 the E2 square divided by R2 square the plus, okay, R2 by x2 the into x2 whole square. Now simplify this. So we will get 180 by 2 pi ns the into E2 square divided by 2x2 the 2x12. So in order to get the maximum torque equation, what we have to do, differentiation of the torque with respect to the slip and make equal to the 0, we will get the condition. After getting the condition, then substitute this condition in this torque equation, we will get maximum torque equation. So this torque you can say that the maximum torque of the motors, okay, T maximum values. Okay. So this was my 10 questions in the concept of torque slip characteristics of the 3-phase induction motor. I hope you got it. Thank you very much.